using the Memorize Ion sheet. And in the Memorize Ion sheet, I want you to be looking right up here at the very top. So if you don't have that, turn the video off and get one of these sheets and come on and turn it back on, and we will look at this together. So, first of all, I was going to ask for everybody in this column, what is the charge going to be?
3 plus.
Oh, you hear my very intelligent, studied class. They are so good at this now. Okay. And now, anybody in this column, what is the charge going to be? 1 plus. Yes. And how about this guy?
2 plus.
Oh, my heavens. Okay. And what about this column?
2 minus. 1 minus.
1 minus. And here?
2 minus. 2 minus.
Okay, that sounds a little weird, doesn't it? Okay, let's see if we can figure out exactly what it is that I am talking about. As we go from any one of these guys, let's go here. If I am trying to get to stability, oh, stability, yeah, stability, yeah. There ought to be a law about stability. Yeah. Anyway, all of you watching this video, you know what kind of teacher I am now. Not to be trusted. Anyway, moving right along. So this guy right here, beryllium, when he forms an ion, what is stability for beryllium? Oh, helium. See, if he were going to neon, he'd have to gain 1, 2, 3, 4, 5, 6 electrons. It's not going to happen, folks. It's just not going to happen. So, what he's going to do is he's going to go from here. He's going to lose 1, 2, and button my shoe. No. Anyway. Oh my. I shouldn't be making a video today. Alright, helium. Helium dude. So, he doesn't have 2 protons. He does not have 2 protons. He has 4 protons, but he has 4 electrons. And because the electrons are more numerous than the protons, he winds up with a negative, or a positive charge. The protons are more numerous than the electrons, I should say. Because he starts out with 4 electrons, he loses 1, 2, and now he has 2 electrons, but he has 4 protons. Yes? Essentially. Yeah. Groups 1, 2, and 3, you're always going to lose, because you're metals. Metals are a big bunch of losers. You see this whole area here. These are all metals. And metals are losers. What do they lose? Electrons. Okay, and so the guys over here, these are our non-metals. I call them a den of thieves because they steal electrons. Okay, and they steal electrons. Why? To get stability. Yeah. Oh, yeah. Anyway, so what does sulfur get for getting stability? What does he have to get stability? You got it. Okay, what does bromine have to get to have stability?
1 electron.
Yes, and stability is good. Yes. Okay, when you gain electrons, when sulfur gains electrons, sulfur, the atom, has 16 electrons to match his 16 protons. But sulfur, the ion, has a situation where he has 6 valence electrons. 1, 2, 3, 4, 5, 6. Because he's 6 over on principal energy level 3. right? So because he has 6 valence electrons, if he gets 2 more, he'll have 8. And that's what stability is all about. That's what it's all about. Boop. Yeah? Are you okay with that? Stability is 8 electrons in the valence shell, except for helium. Helium and hydrogen are kind of orphans on the chart. They don't really belong anywhere. Okay? Hydrogen kind of belongs in column 1 because if he forms an ion, it'll be a what? It'll be a 1 plus ion because he's going to lose an electron. Yeah, you see, it doesn't work. Yeah, it doesn't work. So it doesn't work also because this hydrogen dude is sitting here in this column with what we call the alkali metals, right? Group 1. So he's obviously not a metal. He's a gas. Yeah, at room temperature. He can be made into a solid, but a very poor excuse for a metal. Yeah, just not a metal. Okay, so helium likewise doesn't have 8 electrons in his valence shell. He's only got 2. And 2 protons will not support 8 valence electrons. They don't have enough tug to keep those electrons on the nucleus. Okay, or around the nucleus. So, like I say, helium and hydrogen are kind of orphans. But let's move on now and let's see on what I've done on the smartboard for getting you a better understanding of how to treat these guys. First of all, let's get rid of all this stuff. So, what I've done here is I've made a graphic where you can see a little chart that has protons here, and protons never change. In chemistry, that is. In nuclear chemistry, yeah, protons change. And when they do, look out. You better be many miles away. I mean, many miles away. Even if you don't get hit by a nuclear blast, the fallout will get you. If you're anywhere near it. Yes. Hiroshima. Yeah. Oh yeah. That's a big boom. Very big boom. Anyway, so this guy is solid. In my graphic here, when I try to move it, it doesn't move. However, what does change within the atom are the electrons. So if electrons change, then I can move them up or down according to how many electrons are gained or lost. So let's go to beryllium. Would you look at your chart and tell me, what do you have for the charge on beryllium? Beryllium is number 4 on the chart. 2 plus, excellent. Okay. And how about antimony, SB? That dude is number 51.
We don't know.
Yeah, you do. Yes. What would you guess? 5 plus or 3 minus?
3 minus.
Because it's an easier task to gain 3 than it is to lose 5. So, SB is going to be what charge?
3 minus.
3 minus.
Yeah.
There you go. Now, let's look at what that means. First of all, for beryllium. Beryllium, the atom has an equal number of protons and electrons, as you're seeing in my little graphic right now. Okay. So, when we make him a Be2 plus, what do I have to do to the electron slider?
Move it up.
Move it up. Move it up 2, and that gives us a what charge? 2 minus, yeah. Because I have 2 more electrons than I have protons. Now let's look at the antimony. 3 minus. Whoops. We went the wrong way. Beryllium? No, this goes down. It becomes positive, not negative. the pile of electrons actually goes down because beryllium has a positive charge. He has a positive charge because he loses electrons. And so, as you can see, my pile of protons stayed the same, but my pile of electrons went down. I've been trying to say this with hand motions, but it just doesn't mean the same as it does when you put it on a chart like this. Okay, so that was my beryllium. Now antimony. No, it's not +1. It's a 3 minus. So how many extra electrons does he have? 3. So that means we have this situation. The electrons have gone up to 3 extras. So we have 3 more electrons than we have protons, and so the charge is 3 minus. Isn't this nice? This is the first way I've taught this in this manner. And it seems to be making sense to a lot of people. Unfortunately, period 1 and 2 didn't have the opportunity to see it right this way, but I was close. And by the time I got through period 5, I had a pretty good idea of how to do this. And so you're getting the benefit of that. All right, so now that we kind of are getting this concept over here and why these charges are what they are, now we can actually see how to write the formula for the molecule that they will form. So I'm going to put a BE down here, and I'm going to put an SB over here, because BE is always first because he's what? What's his charge? Yeah, he's a positive. Positive ions are always first. Write that down. That's good stuff for your notes. Positive ions are always written first. 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 Write it. Positive ions always come first in a molecule. Yes? It's not weird at all when you look at the slider. Okay, the question was, say it again. State the question again. You're just not switching gears to the negative. Okay, if we lose electrons, that means our pile of electrons is getting smaller. And I have more protons than I have electrons. Can't change the protons. However, if I gain electrons, yes, I'm adding to the electrons, but adding electrons makes me more negative. Because I now have more electrons than protons, the way the slider is set now. Yeah, this really is solid. It helps you stay oriented. And I hope it makes more sense to you now. Let's try now to figure out what the numbers are going to be to get this to be a balanced molecule that has a 0 charge. Okay. What we do is we look at, let's go clear over here. There we go. Okay. This 3 comes over here, and we use the absolute value to get the subscript. So what's my subscript? 3. And this 2 comes over here to the antimony to make the subscript for antimony, which is 2. No, it's not minus. It's only absolute value. Absolute value is always positive. Okay, now, here's how you check yourself. And watch what I'm doing. I'm grouping the antimonies first as the ion, which you see up here, and then as to how many we have. Here's the charge on the ion of beryllium. Here's how many berylliums we have. So I'm going to block that out as well. And now, start with the subscripts. And we have 3 berylliums. What's the charge on beryllium as an ion? 2 plus. So we're going to have a 2 plus here. And what's our total? 6. 6 plus. All right. Now, how many antimonies do we have? 2. Times, what's the charge on the ion? 3 minus. And that's going to be 6 minus. And this is what we have to always get, net zero. Okay, just like the internet provider. Net zero. So, are they good? Net zero? Anybody have net zero? No? Anyway, so this is what you're always after. Now what I'd like you to do, and I'll stop the recording. You need to stop the recording if you're watching at home. What I want you to do is try the rubidium-selenium combination and see if you can get that to come out right. And okay, here we go. David, would you tell us, what do you have for a charge on rubidium? Good. Okay, so rubidium, I'm going to go through this. I'm going to go through this quickly with each of these ions, just to remind you that we have lost 1 electron, and that's because our protons don't change. The proton pile is now larger. Okay, and David, what do you have for the selenium? 3 minus, okay. And how should I... Whoa, no. You're column off. It's 2 minus. Okay, because he's in column 6. And if he got 3 electrons, he would be past stability. And he'd have no motivation to do it. No, he would not be super stable. He'd be super unstable.
What would happen?
Yeah, what? Not radioactive. He'd just be horribly reactive. Oh, he'd be nasty. Woo. He would come up and blow you right off the table. Yeah. Now, let's do selenium. Selenium, our pile of electrons is 2 more than we have protons. And because selenium is element number 34, he would wind up with 36 electrons, which makes him look like krypton for his electron configuration only. Okay? And, okay, Gavin, what do you have for barium? Uh-huh.
Barium is 2 plus.
2 plus. And how about sulfur?
2 minus.
Okay. By the way, David, let's write the formula for rubidium sulfide. Yes, Rb2 because of this guy, and Se because of this guy. But you do not write a 1. 1s are... No, it's not an option.
There's always going to be...
Well, a little stinker. Steve. Bad dog. Okay. Anyway. Kevin, let's go down now. Okay, to get the barium sulfide right now, we have to look at barium. And when we do the barium, we look over at sulfur's charge. And we use that for the subscript. Remember, it's absolute value. And then we do sulfur, and the sulfide ion winds up having the 2 minus charge, so that's a 2 also, or the 2 plus, I'm sorry, 2 plus from the barium. But you'll notice that we have a ratio here of 2 to 2. That ratio of 2 to 2 means that it has to be simplified. So you might think, okay, well, then I'll do it barium 1, sulfur 1. No, that's a no-no. We don't write 1s, so the actual formula that you need to have is barium sulfide. And the other 2 no good, okay? Because we want the smallest possible ratio between the barium and the sulfide. And basically, whenever you see the charges are the same, like here and here, that charge being the same tells you that you just need one of each, because what is your ultimate goal? Your ultimate goal is to get a net zero. And so, as you will see, here with the, first of all, with the rubidium and the selenium that we did over here, as we go over here to the right to test it all out, we look at our numbers, and you can see selenium and rubidium in the ratio of 2 to 1, rubidium to selenium ratio. So I take the subscript, which is 2 for rubidium, the charge, I multiply by the charge, which is 1 plus, that's the charge on the ion. You notice we don't write charges when we actually do the molecules themselves. See these molecules? None of them have a charge in them. Okay. And this guy down here doesn't have a charge in. So, at any rate, we continue to get the numbers, and we wind up with a 2 plus. And then when we do selenium, the subscript is assumed to be 1 because it's not written there, times the charge on selenium, which is a 2 minus, which gives us a 2 negative, and our total winds up a net 0. And last one, I'm just going to do one more time here with the barium sulfide. And let's go ahead and make a little more room down here so you can see what I'm doing. Okay, barium has one barium, and the charge on the barium ion, which we see up here, is 2 plus, times 1 is 2 plus. And then the sulfur up here has 1 sulfur in the molecule, which we see here, 1 sulfur, times the charge of 2 minus, and that equals 2 minus, and we net out 0. And so that's it, folks. That's how you do this stuff. And I'm just going to go back and give you the answers that I had for the do now. And with sodium at 1 plus and nitrogen or nitride at 3 minus, we have Na. We have to have 3 sodiums to have 1 nitrogen, because nitrogen gives us 3 negatives, and it takes 3 of these guys to balance it with 3 positives. And likewise, lithium has a 1 plus charge, oxygen has a 2 minus. So doing the crisscross, using the charges to get our subscripts, we have lithium sub 2, that means there's 2 lithiums, and 1 oxygen. So that's it. I hope you've got it down now. Thank you very much for watching.